Hello everyone. Um, Now I am going to discuss a lecture on single phase AC to DC converter with R load. And here, first, when I am going to discuss about the topic, first we have to know the importance of AC to DC converters. Here, AC to DC converters, basically AC to DC converters are used for many applications. Importance of AC to DC converters. First, AC to DC converters. What is the use? We will see AC to DC converters. First one, we are going to use it in like renewable energy systems, renewable energy systems. Next, second one, smart grid systems, smart grids. And third one, UPS. Fourth one, medical applications. And finally, fifth one is communication systems. So these all the major applications we can see for the AC to DC converters, which is represented over here. So these are the basic applications where we are using the AC to DC converters. Now AC to DC converters are different types are there. In that one, first one is AC to DC half wave, AC to DC full wave, and AC to DC three phase half wave, three phase half wave, next three phase full wave, three phase full wave. In that one also we can refer that R load, RL load, and RLE load, RLE load. Now in this lecture we will see single phase. Now in this lecture we will see single phase AC to DC converter, single phase AC to DC converter with R load, with R load. Here single phase, we are using only one phase. Here AC to DC conversion, and here with R load. Here AC to DC conversion. This is single phase half wave. Sorry for the disturbance. Single phase half wave AC to DC converter with R load. Now we will hear half wave. It is indicated that half wave, it indicates half wave indicates that we are going to control only 0 to 180 duration waveform, and after that it is not going to control. This is 0 to 180 controllable, and 180 to 360 uncontrolled. Here only one half cycle we are controlling. That is why we call it as a single phase half wave AC to DC converter with R load. And here 0 to 180 degree only we are going to have different types of operations. For suppose resistive load, inductive load, RL load, and RLE load. RLE load. Now, if you refer the structure if you refer, first we will take a AC source, that is 230 volts, 50 Hz. Vs is equal to Vm sine omega t. So this is the basic circuit which I am going to draw here. Just observe that here we are going to use one SCR, and after that we are going to use a resistive load, and after that we are going to connect it over here. Now this is load. Let us indicate that this is R load. This is plus and this is minus. Current flowing through the resistor is I naught, and voltage across this resistive load is V naught. V naught. Now this is the SCR, means we have to take three terminals. which are which are which are here. If you take here, if you take here, if you take this is anode, this is cathode, and this is gate. Now we'll see step by step operations. What are the possible waveforms here? Source voltage one waveform, and along with that thyristor gate signal one more waveform. Here gate signal is nothing but activating the switch step by step 0 1 0 1 0 1 0 1. Like that we are going to operate the switch. Now let us take it as a waveforms. First we will take the waveforms. Step by step we will draw the waveforms. First check that how we are going to draw the waveform here. First to take the waveforms. First we will draw one vertical line that will be based on that line we will draw the waveforms, step by step waveforms. First we will take it as a source voltage. Let us take it and divide it into many parts. One pulse 0 to 180, after that 182, 360, 362, 0 pi, 2 pi, next 3 pi, next 4 pi. So here there are 4 pi waveforms. Up to 4 pi we are going to take 0 pi, 2 pi, this is 3 pi, and this is 4 pi. So here exactly at this position, exactly at this position we are going to give the triggering pulse. That is why I am taking a triggering here, triggering angle. And coming to this is the uncontrolled. This is we are not going to control. This is uncontrolled pulse. Again here we are going to control. That is why I am giving a switching pulse. That is pulse here, and after that this is also uncontrolled. For that we are going to observe the waveform. Just to drag a line at exactly 180 degrees so that you can observe the waveforms how the thyristors silicon control rectifiers are activating towards to the different waves we can observe here. Now let us take it as a 0 pi 2 pi 3 pi, those things we can draw here. Now this is first one is Vs source voltage, that is if you take it over here. Exactly, it is what is this? This one is Vs is equal to Vm by Vs is equal to Vm by root 2. And coming to this is Vs. And this what is this? This is Vz, switching gate pulses. And now what we are going to do here? We are going to draw the output waveforms, and this is a resistive load. Am I right? Then that is the case. Voltage and current both are in phase. Then that is the case. First, draw the vertical line at switching pulse, whatever it is given here. Then here there is no controlling. From this, you can take a overall signal here. Next, there is no controlling signal. Now indicate that this is 0, this is alpha, this is pi, this is 2 pi, this is 2 pi plus alpha, and this is 3 pi, and so on. Finally, this is 4 pi. So up to this it is clear. Now what I'm going to tell here, V naught, whatever V naught, I naught waveforms are exactly similar, because here we are going to utilize a resistive load. Then that is the case, the waveform here you have to observe that this is here this waveform we are not going to get it output side, because the thing is we are going to give the triggering pulse at only alpha. We are not going to trigger at 0. That is why. So the pulse output pulse waveform. Let us draw a just normal horizontal vertical straight vertical line. Don't draw like a sinusoidal waveform. From here, let us take it as a peak voltage. It will go here and it will go up to this and it will come up to pi. So first positive half cycle, whatever the triggering it is there, this is forward, this is anode means plus minus we are giving here. Then thyristors will get short circuited and whatever the source voltage it is there, it will flow towards to this and it will come to the load. So when it is coming to the load, we have to clearly observe that the waveform will be here. We are going to this clip this part and we are going to get it this waveform. So this is positive half cycle. Positive half cycle means plus minus. Am I right? Then after that, when we are going for negative half cycle, let us take it as a negative half cycle. What will happen here? Instead of plus minus, this is minus plus will come. Minus plus we are applying across the anode and cathode. What will happen? This will be open circuited. Whatever the ACR or ACR or MOSFET or IGBT anything. If you take it here, this is minus, this is plus, then this circuit, entire circuit will be open circuited. Then there is no connection between source and load. That time, what will happen from pi to 2 pi, there is no voltage or current because the reason it is open circuited. Then after that, if you observe that at 2 pi to 2 pi plus alpha, we are not going to give any triggering angle. It means silicon control rectifier will be in, still it is in open circuit condition. After 2 pi plus alpha, we are going to give the triggering angle. Then there will be a voltage existed in the circuit. That voltage only we are indicating over here. So here at this peak moment of voltage, what is the voltage? V naught is equal to here. What we have to measure here? V naught we are going to measure here. That is V naught is equal to, in terms of, take it as an integration. Here most of the people they'll get confused how to calculate the V0 output voltage for the single phase half wave rectifier with R load. Here V0 and I0 waveforms are shapes are same, but the problem is V0 waveform we are going to calculate from 0 to pi, and the current waveform we are going to calculate I naught is equal to V naught by R. Similarly, V naught RMS, how we will calculate V naught RMS is equal to same as it is in terms of time duration, means we will take it as a 0 to t. But here in terms of pi, 2 pi, 3 pi, 4 pi, that is the reason what we are going to do here. V naught RMS is equal to square root of 1 by 2 pi integration of 0 to 2 pi Vm square sine square omega t. Now we'll see the derivation of each of the things. First, before that, I'll show you how this is V naught is clear. Now V naught is everything is clear. Now we will see how another waveforms will come. First, next now V naught I naught is clear. Now, if you people are observe up to if you observe this up to take it as a this line continuously. Now V naught I naught is clear. Now what are the things are pending here? V naught I naught is clear. However, there is a problem. We have to identify that thyristor voltage. So from here, if you people observe clearly, so this is 0, this is alpha. At this position, thyristor is going to switch on. And similarly, here also thyristor is going to switch on. Remaining places, it is not going to switch on. Then 0 to alpha, whatever the source voltage it is there, similar voltage will appear like this. And after that, alpha to pi, there is no voltage. Then pi to 2 pi, as it is voltage will come, because whatever the anode to cathode voltage it is there, it is a open circuited. Then source voltage will be anode voltage. Then after that, if you observe that, then if you observe that, then 2 pi to 2 pi plus alpha thyristor will be in, still it is in off condition. Then the waveform will come like this. So after that again existed, then will be 0. So this is the source voltage, this is the load voltage and load current waveform shapes, and this is the thyristor voltage. So these are the three major waveforms in the single phase half wave AC to DC converter with R load. Now we will observe what is the average output voltage we are getting, what is the RMS output voltage we are getting, and what is the RMS input power and average output current, RMS output current, everything we will observe now. First, from the above waveforms, the average output voltage we will written as V naught average is equal to 1 by, as I told you that this is complete one repetition, right? V naught average is equal to 1 by 2 pi integration alpha to 2 pi Vm sin omega t d omega t. Now let us talk about Vm is a constant. Let us take it as a outside. Vm by 2 pi. Integration sin theta means cos theta. Then we will write as a cos omega t. That is alpha to 2 pi. See, this is here I told you that the waveform it is existing only 0 to pi only, right? Alpha to pi. Sorry, we should not write here 2 pi. We have to write only we have to write alpha to pi. Then that is the case. Remove these two. Then what will happen here? V naught is Vm by here also we are get total duration is 2 pi, but conduction output voltage is alpha to pi only. If you want, you people can observe the previous waveforms. Now, what is happening here? Vm by, let us take it as a Vm by 2 pi. Let us take it as a minus common minus Vm by 2 pi cos pi minus cos alpha. Like we have to apply the integration. Then minus Vm by 2 pi cos 180 means minus 1 minus cos alpha. Then finally, V naught average output voltage it is equal to Vm by 2 pi into 1 plus cos alpha. This is the average output voltage of the single phase half wave rectifier with R load. Now this is the R load, right? Now I naught average will be V naught average by R. So this is the I naught average and previous one is the V naught average. Now next we will see what is the RMS output voltage and RMS current. Now let us take it as a RMS output voltage. This is V naught RMS, root means square value is equal to square root of 1 by 2 pi integration 0 to pi Vs square d omega t. Now what is here? Vs it is nothing but what we can write it here. Vs it is nothing but here Vs it is nothing but Vm sine omega t whole square d omega t. Next 1 by 2 pi in Vm square. Let us take it as a Vm is a magnitude constant. We are not going to change that one. So that is the thing. We are going to write it as a Vm square common. Then 0 to pi sine square omega t d omega t. Next, how we can write it here? Next, that is V naught RMS is equal to Vm square means Vm by square root 2 square root of, how can I write it here? 1 minus cos 2 omega t by 2 integration 0 to pi d omega t. That is the basic thing we have to write. Next, V naught RMS is equal to, let us make it as a 2 will be common, then Vm by 2 will take it as a total value, then we will apply square root of integration 0 to pi 1 into dt minus cos 2 omega t integration 0 to pi dt. Then what will come here? V naught RMS is equal to Vm by 2 square root of 0 to pi means pi minus 0 minus cos 2 omega t means integration of cos 2 omega t means sin 2 omega t by 2 integration we applied 0 to pi. Then what can we write it here? Vm by 2 square root of pi minus 1 by 2 will be the common sine 2 pi minus sine 0. This is the overall thing. So, sorry, here pi minus alpha we have to write, right? Alpha to pi value. Then alpha to pi. Here sine alpha. Then finally what we can write it here? Vm by 2 square root of pi minus 1 by 2 times of sine 2 pi means 0 minus sine 2 alpha. Then the final answer will be V naught RMS is equal to Vm by 2 into square root of pi min pi pi minus pi plus minus into minus plus pi plus 1 by 2 sine 2 alpha. This is the final answer for the V naught RMS. Coming to the I naught RMS, it is nothing but resistive load means V naught RMS is divided by R. That is called I naught RMS. This is V naught RMS. Now, if you people observe that the active power of the source, how we can write it here? P is RMS, source RMS is equal to our source RMS, R P naught output RMS is equal to V naught RMS into I naught RMS. Like this way, you can write the RMS power of the RMS power of the overall load. Now, if you people observe that, for suppose single phase half wave rectifier with RL load, if you people observe that, how it will come? Here, the waveform will be completely changed. And for before going to that, what is the advantages or what first advantages which we have discussed already? For medical application, we are using this, and UPS power applications and as well as renewable energy systems, we are using this type of technologies. Now coming to the disadvantages. So disadvantages, if we observe the disadvantages of single phase half wave AC to DC converter. So, the first foremost drawback of a single phase half wave AC to DC converter is we can control we can control only half of the cycle. We can control only half of the cycle. Second one is when we are controlling only half of the cycle, then we can generate discontinuous we can generate discontinuous we can generate discontinuous output voltages. We can generate discontinuous output voltages. And as we know that THD value is also THD value is also existed in the overall circuit Finally, we can face the electromagnetic we can face the electromagnetic interference issues in the utilized circuit in the utilized circuit. So this is the considered disadvantage of the single phase half wave AC to DC converter, and in that one majorly we can focus that RMS voltage and average voltage we have to focus. Then we have to go through the waveform shapes and all. And coming to the next, we are going to see the single phase half wave AC to DC converter with RL load. How the waveforms and shapes, everything we'll see. We'll observe it. Thank you all. Thank you so much.